Welcome back to Grade 9 Applied Mathematics. We're continuing our work in Unit 6, which is solving problems with linear relations. We're going to now look at Lesson 3, which is going to explore how changes in one representation, so if I make a change to the graph, how might it impact the other three representations that they have here. So we're going to do this one at a time. We'll start with a scenario in which we'll change the graph, and then we'll move to the others. Your class note is going to look like this, and notice that we have a place for you to record notes for each different thing that we're going to be looking at. So we're going to be looking at the diver, then we're moving to a candle, then a bike, and we're going to end in a battery. So you can write your notes or your thoughts off to the side. First thing we're going to do is I'm going to move to my GSP sketch here. And I'm just going to pause momentarily so you can get set up with your notes. All right, so resuming, in our first scenario, this is going to be the diver diving. And the graph is going to drive the other three representations, the table of values, the context, and the equation. And to show you how this works, the green point, if you shift that, it's impacting the y-intercept of the line. And moving the red point is going to impact the steepness of the line. And if I can convert this to JavaScript, then maybe I will upload this so you can practice this on your own. So the first thing I'm going to get you to think about, if I were to take the green point and drop it here, what impact would that have on the table of values? What impact would that have on the context? Then what impact would that have on the equation? And I've changed the units to decameters so it would be more reasonable. On an inexperienced diver, a non-professional diver, the deepest you would go would maybe 120 meters. So a decameter is a tenth of a meter, and that means the scale would make sense, because the lowest we would be going is, before we're off scale, would be negative 120 meters. So if I move this up, let's take a look at what's happening. So we shift it up, and then the initial condition has changed. And the initial condition in the equation is the constant sitting on the end. So this is updated, but the slope hasn't changed. It tells us where the diver is starting, 100 meters below sea level. That's changed, but the rate at which the diver is swimming hasn't changed. Now, taking a look at the table, the table starts at 100. All of these values have changed because our slope, well, let's just take a look at the slope. I'm going to change delta x to 1 just so that you can see what's happening here. So when delta x is 1, notice how the depths drop or decrease by 20. That's how we're getting a slope of negative 20. If I change this to 2, then these are now dropping by 40. So if the slope is negative 20, if you change by 2 seconds, then you should drop by 40 because you're changing your distance by 20 decameters every second. So in 2 seconds you should drop by 40. Now I had this at 5. Why do you think that was at 100? So I'll give you a second or two to think about that. And the reason that's at 100 is 5 time units. We would need to multiply this by 5 to get 5 seconds, and it's dropping by negative 100. So every time time increases by 5 seconds, depth has to decrease by 100. So when we change the initial condition to negative 100, these still went up by 100 from where they were. I'll just drop it back down so that you can see. They're still increasing by 100. Every value is different, though, because I've changed the initial condition. And so changing delta x is just going to change what's happening in the x column. So if I change that to 4, then all of these go up by 80. So if we change the initial condition, we can see where are they represented in the table. It's represented by the green value here. If I want the slope, I have to look at the changes in time and the changes in depth. Delta y's and delta x is written on the bottom, and the initial condition is here. So now what I'm going to do is I'm going to pull this down to there, and I want you to think about what's going to happen in each of our 3 representations over here. And so I'm going to pull it down now. And then what we will see now is the rate of change hasn't changed, but we're now starting 500 meters below sea level. The initial condition changed over here, it's minus 500. And within the table, the initial value or the initial depth is negative 500, and now everything is going down by 40 because, again, time is changing by 5 units, but I could change this to a 3. Let's see if you could figure out what that value would be. Changing that to a 3, then this is going up by, or not up by, but down by 60, because negative 20 decameters per second, if we multiply by 3 to get 3 seconds, negative 20 times 3 gives me negative 60. All right, so I'm going to take the slope one. This is the one that impacts the slope, and I'm going to take it and I'm going to pull it down to here. So which value do you think will change over here? And do you think when the value changes, will it get greater in magnitude or smaller in magnitude? Which values do you think are going to change over here? This one or one of these two values, and which value will change here? I'm just going to keep moving forward, but if you would like more time to think, I'm going to suggest you pause this video on your own. So when we pull this down to here, the line has gotten steeper. Because the line has gotten steeper, the slope, or the rate of change down here, has increased. So instead of dropping at a rate of 20, it's now a rate of 40. Notice how in the equation the initial condition hasn't changed, but what changed was the slope. It's now negative 40. And then over here the initial condition didn't change, but now the rate of change is supposed to be negative 40. So let's see, we have negative 20 dropping by 120 each time, while these are going up by 3. The slope would be negative 120 over 3, which is negative 40. When I change this to 2, see if you can tell me what this should be equal to, given that we want the slope to be negative 40. And now we can see that's negative 80. That makes sense, because if we double 1 second, we get 2. Double negative 40, we get negative 80. What happens if I put a 1 in here? And then I'll hit enter. We should get our negative 40 there. So if you want to get the slope value from here, you're going to need to make delta x 1. Last thing I'm going to try is making delta x 5. What do you think delta y is going to become? And now we can see delta y has become negative 200. So if we start from a graph and I change the y-intercept, then what will happen in all of our 3 other representations is where the initial condition was. The initial condition right here and the initial condition, only the initial conditions change. And I'll just have you take a look at that as I shift this. And now when we change this value here, it's impacting the slope. So if I pull it down, it gets steeper. So we have an increase in magnitude. This has decreased in value. I'm going to show you what it was when it was here. It's negative 60. Negative 80 is lower than negative 60, so it's decreased in value, but it's increased in magnitude, because a magnitude of 80 is larger than a magnitude of 60, and we expect that to happen because this line is getting steeper. And notice when we change the slope, all of the red values are changing, except this one isn't changing. Because it needs to stay constant. We can't change both of these together. One of them has to stay constant so that I can get the correct slope value. So if we are counting, you tell me what you want to count by, then the delta y values are going to go up according to the slope. So if I change this to 2, then that changed to negative 120 because the slope should be negative 60. Now what will happen when I drop this here? What changes did we notice? What's happening to the slope? So the slope used to be, down here the slope was negative, but when I pulled it up to here, the slope has become positive because it has positive correlation. And notice here the diver is now swimming up, whereas here the diver was swimming down. What will happen if I drop it right here? So when we drop it here, I wrote he swims down, but I should really fix that to the diver isn't moving at all. So I should go back and adjust that to say the diver isn't moving. We don't need to write the 0x here. We could just write this as y equals negative 600. And now it doesn't matter what I change delta x to, delta y will always be 0 because our rate of change is 0. The depth is always going to stay constant at negative 600. So that was taking a look at a representation where we make changes to the graph. We change the slope, or we change the initial condition. And then we look at how it impacts a table of values, a context, or an equation. Now we're going to move to the next slide. And actually, before we move to the next slide, I'm going to suggest you come down here. I'm going to do a time to ponder pause because I would like you to fill in. We had a discussion. What happened? What happened when you changed the green dot? What happened when you changed the red dot? You should probably fill that in there. So we'll take a time to ponder pause. All right, resuming and trying making the best of things. This would be easier to do if we were in class and you were able to give me feedback, so I'll try to anticipate where things might be going now. Now, the graph is not the driver. The driver now is the table of values. And notice in the table of values, both delta x and delta y can change. But here, only delta x was allowed to change. So after we choose a delta x, then the delta y will be dependent upon what slope we need. So if we want the slope to be 20 and delta x is now 8, we need delta y to be 160 to get the correct slope. So in this setup here, now we can change delta x, we can change delta y, and we can change this value right here. So what I'm going to do right now is I'm going to change this value to 70. And I'm going to hit enter. I would like you to think about what is going to happen to the graph. Will it get steeper? Will it get less steep? Will it shift down? Will it shift up? Or maybe there'll be no change at all. What's going to happen to the context? Will either of those two values change? And what will happen to the equation? Will either the red or the green value change, or maybe no values will change? And again, if you need more time to think about this, I'm going to recommend that you physically pause. So I'm going to hit enter now. And what happened to the line? I hope you noticed that the line shifted up. The steepness of this line did not change, it just shifted up. Because when you change the initial condition, you're not going to impact the slope. Again, here we've changed the initial condition. We did not impact the slope. And notice how negative is handled by saying it's burning at a rate of. And down here, the initial condition here has changed, but the slope hasn't. And let me just see if I can. I'm going to pause just for a second. Okay, resuming. I just wanted to set it up so I can change these. And see how I'm changing. It's a little glitchy. But do you see how as I change that initial condition, when I make the initial condition larger, the graph shifts up. And when I make the initial condition smaller, the graph shifts down. So changing the initial condition will shift the graph up or down. It'll change the initial height in the context, and it'll change the constant in the equation. Now we're going to set that back to where we started from, which was 60. And then we're going to look at what will happen if I make delta x smaller. So I'm going to make delta x 1. What will happen? Now remember, our slope calculation is made by dividing these two. So what will happen to this line? First of all, will delta y over delta x be larger or smaller than it was before? And remember, before delta x was 2, giving us a slope of -3. Because 2 and down 6 gave us a slope of -3. And then what value will change over here? And I'm going to hit enter now. And then what happens is the slope has become -6. And because the slope that is larger in magnitude, definitely smaller in value, but larger in magnitude, the line has got steeper. And then what happened over here is the initial condition did not change, the rate changed. The initial condition didn't change, the rate changed. All right, so I'm now going to change this to 3. What do you think will happen to the line? What's going to happen to the context? And what's going to happen to the equation? Just giving you some time to think about that. And again, if you need more time, you can pause. We'll hit enter. In magnitude, the magnitude is going to drop because 6 divided by 3 is smaller in magnitude than 6 divided by 1. So the line has gotten less steep because the magnitude of the slope has dropped. It has increased in value because I believe we were at -6 before. -2 is larger than -6, but the magnitude is smaller, so the line has become less steep. So if we increase delta x, it's making the slope smaller in magnitude, so the line is getting less steep. When we decrease delta x, the line will get less steep, because we're making the slope larger in magnitude. And that was too much. We can't go below 1. So, of course, if we divide by 0, we're going to get a slope that's undefined. Now, let's see what happens when we change delta x. So, let's put that at a 2. So, if we make delta x decrease in value, that means I'm dropping it. It's getting steeper, right? Because the magnitude is increasing. So, notice how the line segment is getting steeper, because the magnitude of the slope is increasing. Now, what happens if I increase delta y? So right now, delta y is decreasing in magnitude. It's increasing in value, but it is decreasing in magnitude. And as it decreases in magnitude, it makes the slope smaller in magnitude, so we are getting less steep, less steep, less steep. And right here, when delta y is 0, the candle isn't even burning at all, so I should have set this up so that flame would drop. Now what happens when I keep increasing in value? Now it increases in magnitude, so now the line is getting steeper. And of course, I know this isn't possible because a candle can't increase in height, but we are definitely getting a steeper line now because the increasing y is causing an increase in magnitude. And I'm going to run through this in the negative direction. Decreasing y is right now decreasing its magnitude, causing the slope to become smaller in magnitude, so the line is getting less steep. That happens until we get to 0, at which point we have a horizontal line. And then when I keep decreasing y, it will increase in magnitude. So it's increasing in magnitude, thus making the magnitude of the slope larger, which is making the line steeper. All right, so let's put this back to something that might be more reasonable. So let's do -8. All right, so hopefully that is making sense to you. If you change the initial condition, it caused the line to shift up or down. When we changed delta y or delta x, it changed the slope. And depending upon what we did, for example, if I increase delta x now, because that's in a denominator, it's making the calculation in its magnitude smaller, so we got less steep. When we change delta y is in the numerator, so if you make delta y smaller in magnitude, the line gets less steep, but if you make delta y larger in magnitude, it makes the line more steep. And then given the context in the equation, changes to delta y or delta x impact the slope, so it'll impact the slope values over here. Let me change this back to +4. I just didn't check to see. So this says burns at a rate of -2. And again, I said this context doesn't really make sense. That would mean burning at a rate of -2 would mean you're growing. But the text seems a bit odd to word it that way. And right now we've changed the slope here to a +2. If we change the initial condition over here, then what happens is the initial condition changes here and here. And the initial condition, of course, is changing here, causes the graph to shift up or down. So what I'd like you to do now is sort of summarize the key ideas there. Changing the table of values, and think about how we changed delta y and delta x. We talked about a lot of interesting things here, and changing that initial condition. What happened with the other 3 contexts? Again, a time to ponder, pause. Okay, resuming. Hopefully you created a nice summary of those things. Now we're going to look at the next scenario or context. And in this scenario, it's the bike scenario. And let's see who's the driver this time. So the graph is not the driver. The table of values is not the driver because I can't change that number. And I can change delta x, but notice when I change delta x, it's not changing the slope. So let's undo so that we can see. -50 divided by 5 is -10. If I change this to 1, slope is still -10. If I change it to 2, dividing those two, it's still -10. If I change it to 4, the slope is still -10. So the table of values isn't driving anything. What's the driver in the bike context now is the equation. So I'm going to change this value right here now to -20. And you're going to think about what will happen to this table of values. Will it still start at 100? Will it still go up by 40, or not up, will it still drop by 40 each time? Will it says the bike is 100 meters to the right, will that change, or will this change? The bike is moving backwards at a rate of 10. All right, so I'm going to change that now, and we're going to see what's going to happen. So because that was the slope, let's see what happened. It made the line steeper. Why did it make the line steeper? Because the previous magnitude was 10, and the new magnitude was 20, so it increased in magnitude, making the line steeper. In the table of values, it's still starting at 100, but it can't drop. It was dropping by 40 before, but now it has to drop by 80 because we've made it twice as steep. So our calculation here is now giving us negative 20. If I put a 1 there, maybe you can see that easier if we just leave that as a 1 now. Dropping by 20 each time. And what happened now, this has changed to the bike is moving backwards at a rate of 20 meters per minute. So what will happen if I change this to negative 5? What's going to happen to the line? What will happen to the table? What will happen to the context? And again, if you need more time to think, please feel free to pause. I'm going to hit enter now. And what happens is, in magnitude, negative 5 is smaller in magnitude than negative 20, albeit negative 5 is a larger number than negative 20. It's smaller in magnitude. That caused the line to become less steep. And remember, in our context, the negative is really telling us that it has negative correlation. So we are moving at a slower rate now, 5 meters per minute, still going backwards. Before we were 20 meters per minute backward, so the line has become less steep. In the table, it's still starting at 100, but now it drops 5 every second, whereas before it was dropping 20. All right, so now that we've seen what's happening here, I'm going to change this to 15. What will that do to the context here? What will that do to the table of values? Right now the table of values is dropping by 5 each time. The bike's moving backwards at a rate of 5 meters. This line has negative correlation, and look at its steepness. So when I change it, what will happen to the steepness? Will the initial condition change? What will happen to this table, and what will happen here? And again, if you want more time, feel free to pause. I'm going to hit enter now. So hitting enter, what's happening? Well, first of all, the line got steeper. 15 has a larger magnitude than 5, or negative 5. 15 has a larger magnitude, so a magnitude of 5 versus 15, it got steeper. Now it has positive correlation because I changed it to a positive number. Before it had negative correlation and it was moving down to the right. What's happened in the table now? The table was dropping by 5, but now the table has to go up by 15. And now instead of saying the bike is moving forward or backwards, it is now saying the bike is moving forward because the rate of change was positive. So I'm just going to pause momentarily. All right, so I've got this set up so that it would drop by 2 each time. Let me just hit enter on that. And now what I'm going to do is I'm going to decrease that in value. And notice how I decrease it, the line is getting less steep. Watching over here, this is changing. The slope is changing. They all need to match the 10 here. I think what I'm going to do is I'm going to change this to 2 just to allow you to make a slope calculation by dividing those two. So this still has a slope of 10. Back into here, decreasing it again. The line is getting less steep. The bike is still moving forward, less steep because the magnitude is decreasing, less steep. And now the magnitude is decreasing, less steep, but right now we're not moving. So it would be better if this said the bike isn't moving. We're getting our slope calculation of 0 here. 0 divided by 2 is 0. Now what happens if I drop it one more time? So now it's getting more steep because negative 2 has a larger magnitude than 0, and now this is noting backwards. So that's the impact changing the multiplier in front of the x will have. It definitely impacts the slope, so it's impacting the steepness of the line. It's impacting the rate of change over here. Backwards will change to forwards when the rate of change is positive, and as long as the rate of change stays negative, this will say backwards. This is going to tell us when this is negative that this should drop. This should drop by 4 for every 1 unit of time, but now time is in 2 units, so this is dropping by 8. When correlation is positive, then this is going to go up by 8. All right, what we're going to do next is we're going to change this initial condition. I'm going to change the initial condition to 200. When I hit enter, what do you think will happen to the table? Will delta x and delta y change? Will every value in the table change? What's going to happen over here to the graph? I'm going to hit enter now. So what has happened to the graph is its steepness did not change, it simply was shifted up. That whole graph got shifted up by 100 units. Nothing happened for the rate at which the bike is moving, but the initial condition changed. Delta x and delta y didn't change, but the values in the table have changed now because it was starting at 200, so the next one couldn't be 108. It now has to be 208, 216, but it's still going up by 8 each time because time is going up by 2. And our slope hasn't changed over here. So what I'm going to do is I'm going to pop into this again. I'm just going to see if I can change it this way. No, I'm going to pause because I want to change the values. All right, I want to change it by larger increments. So allowing it to change by 10. You can see now that the y-intercept is increasing in magnitude. Not increasing in magnitude, it's increasing in value and magnitude. But as the y-intercept increases in value, the line gets shifted up. The start point changes, but we're still going up by 8 for every 2 units of time. The initial condition is changing here, and the initial condition is changing there. Now, when we decrease the value of the y-intercept, and I'm not worried about magnitude here, I'm just worried about decreasing the value. Let's ignore the glitches there. I don't know why that is flashing. But notice how the steepness of that line is not changing. The line keeps dropping. So if you make the y-intercept lower, the line will shift down. When we made the y-intercept larger, the line shifted up. And in the table of values, this will reflect the correct starting point, and then the changes in the table of values, how we're moving up, will be determined by the slope. All right, I think that will do it for that one. So we're just going to come over here, and I'm going to remind you just to summarize. We changed these values in the equation. What impact did it have on the table, the context, and the graph? Time to ponder, pause for you to write a summary there. All right, resuming. Hopefully you wrote a nice summary, and now we're going to look at the last context. So in the last context, in the last scenario, it is now the context that is going to drive everything. Notice the changes are over here. So what will happen when I change this number in here? Change that to 1.2. All right, and now let's just start changing that number. So you can see when I increase the initial condition, and of course I've changed it to initial condition, that wouldn't make sense because the capacity of the battery looks like 1.5, right? So if it's 1.5, I really couldn't jump out to 1.9, but let's just ignore that anomaly. Notice how when I increase the initial condition, the line shifts up. When I decrease the initial condition, the line shifts down. The initial condition is reflected in here as I change the initial condition. Notice how it updates. In every value in the table is updating as well. And in the equation, the only thing that is changing is the constant. And now, how do we determine what we're going up by in the table? That's certainly not determined by the initial condition. It's determined by the slope. The slope currently is dictated over here. It's negative 0.1 volts per hour. And notice if you take negative 0.2 and you divide by 2, you get your negative 0.1. I can update that to a 1, so now you can see the negative 0.1. If I change that to a 4, what do you think will happen? That changes to negative 0.4. If I change this to a 6, that changes to negative 0.6, and so on. So no new information here. The initial condition is going to shift a graph to up or down dependent upon whether you're increasing. Right now I'm decreasing the initial condition, graph shifts down. Now I'm increasing the initial condition, the graph shifts up. The only thing changing here was the constant, and again, what was changing here was the initial condition, and then the slope dictates how I should move to the next one, so all values in the right column ended up having to change. All right, let's take a look at the slope now. So I'm going to hit enter on the slope, or the rate of change. Now, I'm changing the rate of change. Actually, I'm going to make us consume power at a greater rate. So the slope is increasing in magnitude, and notice the line is getting steeper as the slope increases in magnitude. The line gets steeper. What ends up happening in your table? Just change this to a friendlier number. So what's happening in the table? The delta x didn't change. It is still 6. But now I need to jump by 0.4, negative 0.4 times 6, which is negative 2.4. So now our voltages need to drop by negative 2.4 for every 6 units of time. Let's change delta x to a 2. And now it's changing by 0.4 each time. And of course, I get it doesn't make sense for the voltage to become negative. But for the purposes of analysis here, I'm adding those extra rows just so that we can see what's happening. Now the voltage is dropping by 0.4 each time because our time is set to be 1 unit. All right, what happens when we decrease the magnitude of the voltage? So I'm increasing the voltage and decreasing the magnitude. Increase in voltage, but it decreases magnitude. As the magnitude decreases, the line gets less steep. All the way up to here, at which point we have a horizontal line, so the rate of change would be 0. Notice in our table the values stay the same. We're stuck at 1.5 volts. 0x wouldn't be written in this equation. It would just be seen as y equals 1.5x. And then what happens if we continue? So now we are increasing in magnitude, so the line will get steeper. And of course, this would be possible if the battery is rechargeable. And notice how the values are going up in the table now rather than down because the slope is positive. And the value changing in the equation is right here, the multiplier in front of the x. All right, so we've gone through all of the context there, and we've talked about now how changing one, either the rate or the initial condition in each context would impact the other 3. So a time to ponder pause for you to fill this one in, and then we'll try some consolidation activities. I am going to pause now. Time to ponder. All right, resuming. We walked through absolutely all of these scenarios now. Now we're going to do some consolidation activities. So a burning candle can be represented by this equation right here. I would like you to think about, if I change the initial height of the candle to 80, what impact would it have on this equation, and what impact would it have on the graph? A time to ponder for you to consider what the answer might be. All right, resuming and taking up the answer to that, that would be the initial condition. So the value here, this is where the initial condition sits. That's going to change to 80. The slope won't change because we're changing the initial condition, and the initial condition has increased. It's gone up. That means the graph is going to shift up. So the line, the graph of the line is going to shift up by 20 units, and I notice the slope won't change. All right, in B, it says back to the original equation, back to negative 15x plus 60. What if the candle burns so that the height is decreasing by 20 centimeters? What impact will that have on this equation, and what impact will it have on the graph? Again, a time to ponder pause. And resuming and taking this one up now. This is a slope calculation. This is the rate of change, so it's going to impact the slope. That's my rate of change. And so the initial rate of change had a magnitude of 15. So we're going from negative 15 then to a negative 20. But I know that's dropped in value because negative 20 is lower. But what matters is the magnitude. The magnitude has changed from 15 to 20. It's gone up in magnitude. So that means the graph is going to get steeper. It's still going to start at 60, but it's now going to be a steeper line. The slope is going to change in the equation, and the slope, because it's sitting right here, we're now going to get a new equation of negative 20x plus 60. Next consolidation question. A landscaping company is charging a fixed fee for a house call plus a charge per plant as indicated by this graph here. If the company decided to charge more per plant, what impact would it have on the graph that's there? And you're asked to draw an appropriate graph. And again, consider whether or not the graph will shift up and down, or will it get more or less steep. And again, a time to ponder pause. Resuming and taking this one up. So charge more per plant, more per, there's the word per, that definitely tells us it's a rate. If we change the rate, we're going to change the steepness. Now they told us they're going to charge more, So if we charge more, it's going to increase in magnitude. If it increases in magnitude, it's going to make the graph steeper. So the steepness of the graph will change because the magnitude of the slope is increasing. Now, I just made a calculation. Initially, coming across here, that's 3 plants, and this change is $4. So the old cost was $4 divided by 3 plants, which I'm rounding to $1.33 per plant. And the old house call was the initial condition, which is right here at 6. So my new line that I've drawn here, I created it so that it has a slope of, so there is my change in 2 plants, and there's my change in cost. That's $4 from 12 to 16. So my cost is $2 per plant. So you can definitely see that that has increased. But the key idea was that graph has gotten steeper. It is still starting at 6. We are not to change that. And anything steeper than the previous line would be acceptable. Now you're going to try B. The company's decided to charge less for a house call. What impact will that have on the graph? And then draw an appropriate graph. And again, a time to ponder pause. All right, resuming to take this one up. If you charge less for house call, a house call is the initial condition. And the initial condition started at 6, and they said they're going to start less. So anything lower than 6, what will happen is the line is going to shift down. It's going to be parallel. So the green line is parallel to the black line, the exact same steepness, but the y-intercept needs to be something lower. And in my case, I've made this new house call $2. So the new house call was $2. So the line starts at 2, but it has the same steepness as before. Notice over 3 blocks and up 2. So over 3 plants and up $4. Over 3 plants and up $4. Over 3 plants and up $4. So I haven't changed the cost of a plant. I've simply changed where the line is starting. The whole thing has shifted down. All right, so hopefully that's making some sense to you. And we'll try a bit more in terms of consolidating. The cost of a yearbook is given by a partial variation. If we change the cost of the book, what impact will that have on the graph? And remember, you need to talk about starting point and steepness. So will the graph get more or less steep? Will it stay the same? Will the graph shift up or down? Or will it start from the same point? Again, a time to ponder pause. All right, resuming to take this one up. So the cost per book, each book, there's that special word, each or per, that is our slope or a rate. So I'm just going to note here that's a rate. If you change the rate, it will impact the steepness. We haven't changed the initial condition. So the cost of the book is a slope. It's going to impact the steepness of the line. We don't know if it should get steeper or less steep because they didn't tell us how the cost was changed. I should note, though, I forgot to write that, same y-intercept. So we are not shifting the graph up or down. We're simply going to impact its steepness. All right, the next thing we're going to look at, well, I'm finishing writing this off, is the fixed cost is going to change. Then what impact will that have on the graph? And then I would also like you to think about what changes would you need to make to the defining equation. Now let's talk in generalities now. Let's say it's y equals mx plus b. I suppose if we wanted to use meaningful variables, it should be cost is equal to m times n, where n is the number of books and c is the cost. All right, another time to ponder pause. We're resuming to take this one up. So the fixed cost is the initial condition, or the starting point. So if we change that, we're going to impact the y-intercept of the line. So what we're going to be doing is shifting it up or down. So the line will be shifted up or down depending upon whether we increase or decrease that fixed cost. What I haven't written here that I should have written is it has the same steepness, because we didn't change the rate or the cost per book. All right, what changes will be made to the defining equation? The b value or the constant in the equation will need to be updated. So if we had cost is equal to m times n, the number of books, plus b, this is the value that will be updated or changed based on changing the fixed cost. All right, next example. I think this is our last one before I will assign the rest for you to work on. The cost of a yoga class is given by a direct variation. If we want to change the relation so that it wouldn't pass through the origin, so it's a direct variation, which means it's going through the origin, what do we need to alter? What do we need to change about this in order to get a partial variation? And again, a time to ponder pause. All right, resuming and taking this one up. Right now, the cost, if it's a direct variation, it's only dependent. There's just a charge per class. So I presume you would tell them you want to join and you just show up, and every time you show up, you just simply pay a cost for the number of classes. If we want it to be a partial variation, then we're going to have to change this so that the cost is comprised of a one-time membership fee and the cost for the number of classes that you attend. We have to change the initial condition. If it passes through the origin, currently there is no membership fee. To become a partial variation, we need to add a one-time payment for a membership fee, and of course we would then need to have a cost per class. If we simply had a membership fee, I'm going to change the color here, and no cost per class, it would look like this, a horizontal line. Maybe pick a number that I might make sense. Maybe we would say you pay $1,200 and then you can show up an unlimited times. That's what that would look like. Let's suppose we do the opposite of that and we say there is no membership fee, you just pay every time you go. Then it starts at the origin, and then we'll have a line, and the slope of that line would represent the cost per class. Now what if we have both? So if we have both, then we're going to be a partial variation, and we need to have a positive slope. A positive slope because they're not paying you to attend classes, you're paying them to attend classes. This one wouldn't make sense if we did this, and it's coming down. So there would be a membership fee, but now what this would say is your costs are dropping, which means they must be paying you to attend classes, and that doesn't make sense at all. So on this particular sheet here, we've now done all of these pages. We've answered all the questions here. And then there were some multiple choice questions and some other questions for you to look at. So I'm going to suggest you try those, and the solutions to these will be posted online. That brings us to the end of our lesson, exploring the changes in the different representations. Wrapping your head around changing a rate of change or initial condition, and the most common kind of question you'll see is what impact would that have on the graph. So if you made it to the end, thank you for watching. Don't forget to like and subscribe, and as always, take care and stay safe.